When theoretical physicists calculate an answer and the result is infinity, they don't celebrate, they panic. In the math of reality, an infinite result acts as a warning that the laws of physics are breaking down on the page. Look at the Large Hadron Collider at CERN. When researchers used our current models to calculate the vacuum energy density of the universe, the underlying background energy that exists even in empty space, the equations spat out a number 10 to the power of 120 times larger than observed reality. The calculations simply diverged. The same thing happens when cosmologists try to compute the singularity at the moment of the Big Bang. The physical density becomes so concentrated that the math crashes entirely. Modern computer models literally halt trying to process it. Or take this spiral galaxy. The stars at the outer edges are spinning far too fast for the gravity we can see to hold them. To keep the equations from falling apart, we have to add vast, invisible quantities of dark matter that have evaded every detector ever built. Faced with these impossible numbers, the reflex is often to fight the math. Scientists assume the universe is hiding secret particles, rather than questioning the actual tools they are using to measure it. We often treat infinity as a mistake that needs to be contained within our standard four-dimensional frameworks, but infinity might actually be a message. Theoretical physicist Atmaban Pandit proposed a different framework built around a specific idea, the broken ruler. In this view, an infinite result means a measurement tool has been pushed past its dimensional boundary. The universe isn't broken, the ruler is just too small to fit the geometry. To see how this works, we can look at an analogy from Richard Feynman. Imagine an ant trapped on a Mobius strip. From the ant's perspective inside that two-dimensional space, the surface is infinite. It walks forward forever, counting a single side that never ends. Once you step into one higher dimension, the mystery vanishes. You can see a complete, finite shape. The ant's infinity is just a byproduct of its limited perspective. Apply that logic to the Big Bang. In four-dimensional general relativity, as the volume of the early universe shrinks toward zero, the density calculations shoot toward infinity. The math reaches a dead end. But that is a four-dimensional measurement. If you step into a fifth dimension, you encounter the Bekenstein bound, a limit on how much information a region can hold based on its surface area. In 5D, there is a specific, finite ceiling on density. The early universe hits that ceiling and bounces. The universe survived the beginning of time because it had a geometry we couldn't see. Our four-dimensional ruler simply ran out of inches. This dimensional shift also clarifies that vacuum energy error. That mismatch of 10 to the 120 is essentially a bookkeeping error. For decades, physicists have been taking the vacuum energy from every quantum scale and summing it up into one single overarching account. Pundit's scale ladder framework assigns each physical scale its own specific dimensional boundary and energy limit. When the math is applied correctly to each scale, the massive disaster resolves into a balanced equation. The same logic applies to the magic numbers of physics, like the fine structure constant. Its value, roughly 1 over 137, governs electromagnetic interactions, yet its origin has remained a mystery for a century. This number is a direct mathematical shadow. If you take a 120-node icosahedral lattice in 5 dimensions and project it downward, the four-dimensional shadow it casts gives you that constant exactly.
We see this shadow logic in the spinning edges of galaxies as well. When you map 175 different galaxies, the rotation data fits perfectly without needing to invent dark matter particles. The gravity we observe in 4D is being shaped by a 6-dimensional geometric gradient. What we've been calling dark matter and magic numbers are artifacts of trying to understand a multidimensional object by only looking at the flat shadow it casts in our world. The true source of this conflict lives at the boundary of the complex plane, the border between real and imaginary dimensions, where quantum wave functions exist. Every quantum particle is rotating in imaginary space right now. The real number line we base our physics on is just a thin slice of that complex rotation. To truly understand the universe, we have to accept that the dimension we cannot see is more real than the one we can. We have been living in the shadow and calling it reality. However, this framework doesn't solve everything. There is the pion anomaly, a subatomic mass calculation that remains off by nearly 3,000%. Rather than faking a solution to close that gap, researchers have simply labeled the problem open. Honest science requires the humility to know exactly where the current ruler ends. An open problem is a horizon, showing us exactly where the next measurement scale needs to begin. Infinity acts as a milestone. It marks the edge of our current reach and points toward the next boundary, inviting us to build better tools. The universe needs nobody's permission to keep being interesting. We just have to be willing to measure it.